Chapter 7, the quantum mechanical model of the atom. So until the beginning of the 20th century, it was believed that all physical phenomena were deterministic. And what that means is that where something is now, its position and its velocity, predicts where it's going to be in the future. You throw a ball, you can predict where it's going to go. That's good old-fashioned Newtonian physics. That's how everyday large objects behave. And there was no reason to believe otherwise of the very small. But work done at that time discovered that subatomic particles do not act that way. The present condition does not predict or determine the future condition. And the implications of that would be if you shoot an electron down a path and measure where it lands, and you shoot a second electron in exactly the same way, it will probably land in a different place. That doesn't happen with things like baseballs or bullets in a gun. Right? You take a pistol and you shoot it at the target, and all conditions exactly the same. You pull the trigger again, the bullet goes to the same place, right? That's how things work. That's not how electrons work. They follow different rules. So electrons are in a different world, really. It's the absolutely small or quantum world. So these things are so small that they don't obey regular physics. When unobserved, these absolutely small particles like electrons can actually be in two states at the same time. So an unobserved radioactive nucleus can simultaneously be emitting a particle and not emitting a particle at the same time. This is disturbing. So electrons are incredibly small. This is an analogy trying to help you with understanding how small they are. If we took a single speck of dust, a little tiny piece of dust just barely big enough to see, that has more electrons in it than the number of people who have ever lived on the Earth. Billions and billions and billions of electrons in a tiny speck of dust. We just can't get our minds around how small electrons are. So electrons do not behave in the normal way, and electron behavior determines much of the behavior of the atom. And so we have to try to understand what the electrons are doing. We can't directly observe them, and even indirectly observing them changes the behavior. It's so small that when you observe it, the behavior changes. So these things are kind of hard to get our minds around, and so I've got a couple of YouTube videos to help us understand this.
This wouldn't be a YouTube channel without a cat video, so without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option. The powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So that's from a channel called Minute Physics, which has a lot of cool videos. What do you think about that? Can a cat be dead and alive at the same time? No, that's ridiculous, right? And that's really the point of the experiment. This is the thought experiment. No cats were harmed. That it's ridiculous to think about this cat that is dead and alive at the same time. It's not possible because the cat is a regular sized object, right? But electrons don't follow those rules. And so electron or a nucleus can be simultaneously emitting radiation and not emitting radiation. And when you observe it, you force it to be one or the other. It's a little mind-boggling. So here's another Schrödinger's cat video.
Hello and welcome to my...
What?
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more... the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of fucking sciences. So, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Okay, any comments or questions? So, this quantum mechanics business it's very strange, and you're not going to understand it. So, I don't understand it. Einstein didn't understand it. So we just have to be okay with that. Here's some interesting quotes from some of the major scientists who worked on this. Bohr said, "Anyone who is not shocked by quantum mechanics has not understood it." Schrödinger, the Schrödinger's cat guy, wrote, "I don't like it, and I'm sorry I ever had anything to do with it." Right? Albert Einstein attempted unsuccessfully to disprove quantum mechanics until he died. He didn't like it either. He said, God doesn't play dice with the universe. Nobody liked it. So why do we have it? It's because it is how things are. We don't have to like it, it is what it is. So why do we even deal with it? Well, the quantum mechanical model explains how electrons exist and how they behave in atoms. And it explains a lot of things that other theories cannot explain. And even though we do not completely understand how quantum mechanics works, the model is still very helpful. Some of the things that it helps us to understand are things like why some elements are metals and others are nonmetals. Why do some elements gain 1 electron when they form an anion and others gain 2 electrons? Why do they do that? Why are some elements very reactive and some elements are practically inert? They don't react with anything. Why is that? Quantum mechanics can help us to understand that. And also many of the periodic patterns that we see in the properties of elements.